right, we're back at it for the third and final part of the course, part 3. In this part of the course, we're going to talk about polarization, optical instrumentation, and then we're going to talk a bit about quantum optics right at the end, just to show what the cutting edge of this subject is. So today, and for the rest of this week, we're going to be talking about the phenomenon of polarization. Light is a transverse wave, meaning that as it propagates, it wiggles. It wiggles orthogonal to its propagation direction. We've, up until this point, mostly neglected the fact that there's a direction to this oscillation. We talked about it a bit when we talked about reflection off a glass surface, when we looked at the Fresnel equations. And then we had this fact that the two independent directions acted differently. We had the S and the P polarizations. Well, this week we're going to really dig into the mathematical theory of polarization and treat it more generally. Okay, so as mentioned, there's 2 degrees of freedom really. If we have light which is propagating along Z, we can be oscillating in 2 orthogonal directions, X and Y, or some combination of the 2. So light is transverse, and we have these 2 basis states really. We have X and Y, and we can represent any wiggling along this 2-dimensional plane, which defines the direction that the electric field can wiggle, in terms of these basis vectors. So what basis vectors do we choose? Before it made sense to talk about S and P polarization because we had a plane of incidence. But if I just have a beam that's propagating in free space here, there's no plane, there's no reflection that happens anywhere. So what basis should I choose? Should I use S and P, and how would I define those? Well, the typical convention is just to stand up. And horizontally, if you look around, we'll call that one basis. We'll call that the horizontal direction or the X direction, horizontally polarized light. The other direction, orthogonal to that, is up and down, vertically polarized light. And that's the typical basis choice that we use. But we can represent anything in terms of these 2 vectors, right? Anything along the 2-dimensional plane, we can represent as some part X and some part Y. And that's just what we're going to stick to in this course. And so now let's study the evolution of the electric field along this X and Y plane. We're going to call that the polarization. And I need to get something off my chest right at the outset. Remember before we were talking about these plane waves, and we're talking about monochromatic plane waves? But we had light from a complicated source like a burning flame, a star, or a light bulb even. We had a partial coherence. Now it turns out we have the same thing with polarization. Just like we represent our one sine wave, remember this picture we had way from the beginning of the course? Light going like this. We can have light that's due to a complicated source or an extended source of many different subsources or atoms. And that vector, that oscillation, is going to be changing directions randomly. If that's the case, we call the light unpolarized. On the other hand, some sources themselves are naturally polarized, such as a laser. And other sources we can polarize with a device called a polarizer, which we'll talk about a bit today and more next video. But we can have unpolarized light, or more technically, randomly polarized light, where that evolution is not up and down sinusoidally, but is all over the place. We'll talk about that a bit later. Okay, so let's talk about polarization. We can have our horizontal back and forth polarization and up and down polarization. But really, remember we said that these are just 2 basis states. And light is a wave. Light obeys the superposition principle. So we get some interesting stuff when we look at superposition. So here we have some X polarization and some Y polarization. And if we have equal parts, if we just take a vertically polarized light and a horizontally polarized beam and just add them together, assuming that they start out in phase, well, we're going to get evolution like this. Note that horizontally we just have a sinusoidal wave. Vertically we just have a sinusoidal wave. But due to the superposition principle, if we sum them up, we get a new wave, which is, as we see, oscillating 45 degrees to the vertical, or to the horizontal in this case. So this is interesting. Note that the field actually goes to 0 at some point, and it goes to a maximum up here. But this is kind of not that surprising, because we can do a basis change as well by tilting our head at 45 degrees. So if you tilt your head at 45 or negative 45 degrees here, this light will be horizontally or vertically polarized, right? So this is just kind of a new way of looking at linearly polarized light that's going along in a line. So we can always just rotate our bases, and we really have the same thing, okay? So it's just a field that's wiggling back and forth, goes to a maximum to 0 to a minimum to 0. And what we call 0 degrees horizontal, 45 degrees, or 27.2 degrees is just a choice of basis. We can get more interesting things, far more interesting things, when we consider the fact that we might have a horizontal and vertical component to our polarization, and then we can delay one of the beams with respect to the other one. If we delay one of the beams with respect to the other one is not at a minimum when the first one is a minimum, and vice versa. So it never actually would go to 0. Let's actually visualize that and see what we'd see. Okay, so we're going to start off with horizontally. We'll rotate it so we have equal parts horizontal and vertical, and then we're going to delay one of the components, in this case by 90 degrees. And look what we get here. We get what's called circular polarized light, and we can see why. When the two waves are 90 degrees out of phase, one of them is at a maximum when the other one's at a minimum. So the two waves will be doing something like this. They'll be 90 degrees out of phase. And if we use the superposition principle, just add them up, the electric field vector is tracing out a circle in space as it propagates, or as we look at a fixed space, it's tracing out a circle in time. This is interesting. Notice that the field itself never goes to 0. The length of the electric field is constant. And this is a circular polarization. So this is the case when we have equal parts horizontal and vertical polarization, and they're exactly 90 degrees apart. Now that's clearly a very special case. What if we were 62 degrees apart and we had unequal parts of horizontal and vertical? Well, then we get something similar. It turns out we get an ellipse. So the most general polarization state, when the x components and the y components are out of phase by some random value and they have unequal amplitudes, the general case of polarization is an ellipse. So polarization, when we look at these plots, is generally elliptical. By the way, there's a fancy name for these plots. We might have heard of it in Physics 229 electronics. It's called the Lissajous figure, and it's just when you have a x of time and y of time, and you form a parametric plot of the two. It forms up this this pattern here. So the Lissajous figure of the polarization is an ellipse. Now that ellipse can have 0 eccentricity and become a perfect circle, or full eccentricity is at 1. Got to remember my elliptical math. And it will go to the limiting case of a line. So a line and a circle are these special cases of this polarization ellipse, when the polarization is perfectly in phase and plus or minus 90 degrees out of phase, respectively. So hopefully that gives you an intuitive feel about what the evolution of the electric field is and how we can have things like elliptically, circularly, or linearly polarized light as it propagates through space. We'll talk about how we actually construct, how we make this happen in the next video, but for now we have to come up with a bit more of a quantitative understanding of this. So let's look at this plot here. What's going on in this plot mathematically? Remember that we're in three-dimensional space, but we're going to say one of our directions, say z, is where the propagation is going. So we only have to restrict ourselves to a subspace of x and y. And I can write my field as some amplitude in x, some amplitude in y, and they're going to be plane waves. Okay, so x will be a plane wave, frequency omega, with some phase, some overall random starting point, and same with y. And this situation is really what I'm plotting here, is a function of time at a fixed z. Z equals 27, a million, or 0. Doesn't really matter, because that just will be absorbed into the overall phase. So let's factor out everything common to these things. We're going to make a big factorization, and this is what's going on in this plot here. Let's see what we can do to really describe this. So I'm going to factor out a e to the I kz minus omega t plus phi. Let's do that. Plus phi x. And what do I have left? Well, here I just have the amplitude. And here I have the amplitude with a phase. And we'll call phi just the phase difference. So really, we've reduced this complicated expression to just two numbers. These are constants, right, for this field here. I have a fixed phase relation, phi, which is 0.33, about pi over 3 here. And E naught x and E naught y are constants here too. It looks like they're 0.87 and 0.5 in this plot that I've drawn here. So with these two numbers, which you can just call A and B, if we allow them to be complex, or if we want them to be complex, real rather, we just put e to the I phi times a constant. That vector here, this two-dimensional vector, doesn't have any oscillation in it, describes the polarization perfectly. And there's a name for this. These are called the Jones vectors. So again, we're going to start with our electric field as it's defined here, factor out common stuff, and reduce it to the bare essentials. And what we're left with is this vector here. Now, since we're factoring out a constant up front, we might as well, we don't really care about this constant. We're going to factor it all out to 0. We might as well just normalize everything so that a squared plus b squared is equal to 1. And when we do this, we have what are called the Jones vectors. So j here, we're going to call j a times b to e to the I phi. And then we could write a horizontal state like this as just this. It's just only e, right? And a vertical state, this is the vertical state Jones vector, will just be like this. And therefore, you can see as we've have written here, we can kind of do a vector breakdown, a breakdown of how much h and how much v we have. So we can write it in vectorial form, or just, well, I don't know what you'd call this, algebraic form, I guess, and just as a 1/2 a vector form. Okay, so let's look at some of the polarization states that we've already seen of our Jones vectors. So we have the horizontal and vertical ones, which are just as drawn. How about our 45-degree light? Well, that had equal parts x and y, a light, or horizontal and vertical, and no phase between them. The phase between them was still 0, so e to the I 0. And that will lead to the following vectors when we normalize them. 1 over root 2 times 1, 1 for plus 45. What if the other one was the same, but it was negative? So v was minimum when a was a maximum. Well, then it's just going to oscillate in this way, and we have the minus 45 degrees. Notice that just by a tilt of the head, this is the same as the HV basis. These are what are called linearly polarized states. Okay, we can choose another set. So let's look at what we had before with our circular polarization. Now, we've written them as 1 and plus or minus I. But remember, our Jones vector was AB, e to the I phi. And for polarized light, we had phi was pi over 2. And e to the I phi, therefore, e to the I pi over 2 is equal to 1. With a dot over it, is equal to I. And similarly, e to the minus pi over 2 is minus I, right? It's just going to be on the complex plane. It's going to be either here or here. So whether or not it's plus I or minus I just depends on whether or not the light is evolving this way or this way. Okay, so that is the two bases. An interesting thing to note is that the right-hand circular polarized light and the left-hand circular polarized light are also form an orthonormal basis. Okay, so just to kind of briefly go over this point, we can represent any, we can choose either H or HV, plus 45, minus 45, or right and left circular polarized light as our basis to represent anything else. So for example, let's look at a state that's rotated at an angle theta. So we'll call that state theta, which is nothing but cos theta sine theta. So cos theta along x and sine theta along y. So it's going to be some linearly polarized state. There's no e to the I phi here, so it's going to be no phase between them. They're in phase, and the amplitudes are just related this way. So for example, let's choose 30 degrees. Cos of 30 degrees is root 3 over 2. And sine of 30 degrees is a half. So this one would be like 0.866 this way and 0.5 this way. This would be our our 30-degree state. So we can write that vectorially, right? That's equal to cos theta times h plus sine theta times v. That's how we can write the state. Let's actually write this in the right-left circular polarized basis. So notice that, what is right? Right is equal to, remember what it was? It was 1 over root 2 times 1 minus I, and left was equal to 1 over root 2, 1 plus I. So if we notice, we have R plus L here is going to give me 1 plus 1 over root 2, which is this 2 over root 2, it is also known as root 2, minus I plus I over root 2. That's going to give me 0. So if we divide both of these by root 2, we're going to get 1 plus 1, 2 over 2, and 0. That gives me this, h. So h is equal to R plus L over root 2. So we can represent that in different bases. And that's all that we've done here. We've noticed these two breakdowns here, and then we can just plug it in and represent an arbitrarily linearly polarized light which is linearly polarized at some angle, as some combination of left and right circular polarized light. All right, and we're going to use this result a bit later, in video 2 of this week, when we talk about circular birefringence. That is representing polarized states mathematically. Let's talk about manipulating polarized states. So this is more of what we call the Jones calculus. So we have Jones vectors, and now we're going to talk about Jones matrices, which manipulate polarized light. Okay, so the general problem is to manipulate polarized light, meaning going from one basis to another. So we want to go from J1 to J2, or A1, B1 should go to A2, B2. How do you map one vector to another? Well, that's a matrix, a 2x2 matrix in this case. So we're going to, in general, talk about something that manipulates polarization as a matrix. So this is the general setup for a Jones matrix, which takes one polarization state and produces another. And different types of elements will have different matrices, but in general, they're called Jones matrices. So let's take a look at one example, a polarizer. So what does a polarizer look like? Here's an example of a polarizer. We'll play with it in a bit. But basically what this is a device which only lets light through along one direction. All right? So this is what a polarizer looks like. I have a light source which is emitting polarized light, and we'll put in our polarizer. So you can see a lot of the light goes through. But remember that a polarizer lets light of a particular direction through. So as I rotate that polarizing element, the polarizer, for some particular angle, no light is coming out. If I rotate beyond it, light comes out again. And this is how a polarizer works. It's going to block one polarization and let through the other. Initially, we're going to look at a polarizer which is horizontally, only going to let through horizontally polarized light. Next video, we'll talk about how you make these things. So basically what this says is for any arbitrary A and B that does this, right? And if we just perform the matrix math, maybe we can do it by eye. We see that we have to have A times A plus B times B equal to A, okay? And C times A plus D times big D, sorry, B times D should equal 0, no matter what. Right, for any A and any B, we have to get A out, so B certainly has to be 0. And this has to be 0 no matter what we plug in for A or B. So the only way to do that is to set these two equal to 0. And basically, these are all going to be 0, and we should have a 1 there. This gives us our polarizer. But what happens if we're not acting directly along H, right? We need to somehow look at this polarizer in a separate basis. It's going to transmit some light, linearly polarized light at some angle, and block the orthogonal port. You saw just now that I could just rotate the polarizer and change bases. So luckily, whenever we have a vector, a 2D vector, there's a special matrix which rotates the basis. It's called the rotation matrix. And it's just given by this here. Notice that when we set theta equal to 0, we get the identity matrix, as we should. If we set theta to 90 degrees, we get 0, -1, 1, 0, which flips the two components, right? That's the 90-degree rotation here. Okay, in general, we can see that if we apply this to just horizontal light, this has the effect of rotating it, okay? So let's see that. So I have cos theta minus sine theta times cosine theta, and I had horizontal light coming in. Let's see what comes out. Well, I have cosine theta times 0, and I have sine theta times 0, and this is our linearly polarized light at an angle theta. So by applying this rotation matrix, that describes rotating our basis. What about our polarizer at theta? Well, we know what it does very well if we have it horizontal, right? We have a very, very simple matrix if it's horizontal. Our polarizer matrix looks like this. So what we do is we do a little trick. We change bases, we rotate our light, we rotate our heads of our light into the basis where our polarizer is perfectly aligned. So that's going to act on our Jones vector, whatever it is. Okay, so we're rotating our basis, our whole basis, into a particular basis angle where this whole matrix is very simple. And this gives us the answer in that new basis, all right? But we don't get away so easily. We don't want the answer in the new basis. We want the answer in our basis. But that's okay. We just rotate back into our basis at the end. And in general, when we have a given matrix that we want to, we know what the answer is for one particular basis, we can always do this trick where we're rotating it for any arbitrary matrix into a convenient basis and back, okay? This is what is called a unitary transform, and you'll see it a lot in quantum mechanics, but it's useful in optics as well. And kind of hand-wavily, you can say that, well, we're just rotating our light into the basis for which this is simple, applying the operation and rotating it back. Okay, now there's one more thing that we should talk about is unpolarized light. Light can be coherent, it can be polarized, naturally polarized like this laser, or it can be naturally randomly polarized, have a very rapidly evolving polarization vector like this flashlight here. As it turns out, it's naturally unpolarized. But what happens if I send that unpolarized light into a polarizer? Now, remember why we had this interesting polarization state, why we had elliptical polarization in general. It was because of the superposition principle. And this is similar to the way we treated coherent versus incoherent light. When we had a well-defined phase, we could just add the fields, and we had to take care of those interference terms which came up. So for coherent light, we added the fields, but for incoherent light, we added just the average phase. And this is very similar for unpolarized and polarized light. For polarized light, we have this constant phase evolution. And we have to look at what the projection of that phase evolution is onto our polarizer. For unpolarized light, we don't get a superposition state. We have to just statistically treat it. And it's in this case, we say that it's 50% chance horizontal, 50% vertical, or 50% plus, 50% minus, 50% R, 50% L. It's 50-50, equally likely to be any polarization. After the polarizer, however, we've now removed one part of that. We've removed every time the light was randomly polarized along the vertical direction, we've taken it out. When it was randomly polarized along the horizontal, we've sent it through. And what we get that comes through is polarized light. Whether or not it's coherent or incoherent, a polarizer is going to remove half the intensity and it will now be polarized. Afterwards, it's going to be perfectly polarized. So let's have a look at that as well. Okay, so here we have the scene from outside my window, looking at a chicken here. Now, light which is just scattered, or which is sometimes called natural light, is naturally unpolarized. The polarization vector is going to rotate wildly. But we can put in a polarizer to do two things. First of all, we can verify this fact. So as I rotate the polarizer, we should get no variation in intensity. No matter which angle I'm looking at, 50% of the light is along that particular polarization. This is a property of naturally polarized light. The light should also be polarized, so if I put a polarizer in there, a second polarizer, or any polarizer, the light which goes through is now polarized afterwards. 50% of it comes through, but we do have polarized light. So let's try to verify this. We'll put in a second polarizer after our first one and rotate that, and let's see what happens. We'll notice that we now do get a variation in intensity. We can completely block the light, if I can align it properly. We can completely block the light, and we now have a polarized chicken. So light which is coming from a natural source is randomly polarized or unpolarized, but we can always polarize it by putting in a polarizer, getting half the light through. Okay, so last topic for today is wave plates. Now remember we talked about this operational procedure for making circular polarized light. We take horizontal light, rotate it 45 degrees, and hold one of the components back by 90 degrees. Next lecture we'll talk about the physics of what's going on there. But now we're going to talk mathematically how to deal with that. So we want to talk about how to apply a delay along one axis but not the other. And that was in our operational definition of how to make circularly polarized light. So in general we're going to have a setup like this. A delay is just a phase shift. Whether or not it's positive or negative tells us it's a lag or a lead in time. But it's just going to be some overall phase applied to one of the components. So again, we can stare at this vector and find out what we need to happen. So if we stare at this, we see a particular solution. If A is equal to 1, D is equal to e to the I phi, and B and C are both 0, we get exactly what we want, right? No matter what goes in. And this is what we call the wave plate. A wavelength is 2 pi radians. So if we had like a full wave plate, it would delay one of the fields by exactly 2 pi radians, a full wavelength. It wouldn't actually do anything because the thing is periodic to begin with. But more interestingly, we can delay it by a quarter wave. That's 90 degrees. That's that 2 pi over 4, which is pi over 2. That's what we had to make circular polarized light. So this is a quarter wave plate. We delay by e to the I pi over 2, or 100 I. We can also have a half wave plate. And it turns out, this will likely be an assignment solution, that actually serves to rotate our polarization basis. By the way, if we wanted to, this is delaying vertical, leaving horizontal. What if we wanted to delay 37.2 degrees above with respect to 90 plus 37.2 degrees coming in? Well, we just apply our rotation matrix to our wave plate, and that would be the answer we get. Okay, so that was polarization, and let's just summarize. So light is transverse, it's propagating along a given direction, and the description of this Lissajous figure, or the trajectory plotted out by the electric field, actually, as it evolves, is what we call the polarization. And there's a mathematical description of this based on these Jones vectors. Now, we can use this fact that there's 2 degrees of freedom. We have a 2-dimensional subspace that the electric field is oscillating along, and that gave us 2 basis choices. The most typical one is horizontal and vertical, but we can also go plus 45, minus 45, right and left, or we can invent our own bases. As long as they're orthogonal, we'll get the same nice behavior. Now, if I just pick up 2 random numbers and use my Jones matrix to represent them, I'm going to get, with high probability, just some random elliptical polarization. And this is described full well by the so-called Jones vectors, which mathematically represent these, and the Jones matrices, which tell us how to map from one polarization to another. Finally, we talked about 2 tools to manipulate polarization. Polarizers are only going to let one polarization through, horizontal or vertical or some angle in between, whereas wave plates are going to delay one polarization versus the next. And we'll talk about the physics of how you make these things in the next video. And we'll see you next time.